Thank you, everyone. It's good to be here. I'm based in Orlando, so it wasn't too far a commute, but it made me wonder today with traffic as it is here in wonderful Orlando. But anyway, pleased to be here. For Siemens Energy, in the area of CCUS or CCS, more common in Europe, with carbon capture sequestration versus carbon capture and the U for utilization with sequestration, we recognize this is a very fast-moving churn of ideas currently going on, and we wish to participate in all of those. And so our strategy right now is we'll be participating through partners that are developing the end process, and I think I can check through from your list all but one in the areas that we're participating in, at least carbon neutral or even carbon negative range of generating electricity. And I think first off, for me as an electrical engineer involved over the years with development of getting the one commodity, electricity, to the market, everything we deal with is levelized cost of electricity. So for right off, before I start, it's a little bit counterintuitive with some of the other technologies that I'll be quickly walking through today, because there are other offtakes, and all of those are very key from what I've seen for developing a business model with how you're going to achieve either carbon net zero or carbon negative in the capture of CO2. As far as the offtakes, I would suggest that there are, depending on certain states, certain regions in the world, there is a viable market, irrespective of whether a government regional entity is using carrots, incentives, which currently in at least this country have been quite prolific in the last several years, or in going after this with more of a stick philosophy where there's taxation to the emitter level with CO2, i.e. your carbon tax on every airline passenger mile seat in the type of car you buy, anything that's generating CO2. So let's just park both of those at two opposite ends of the spectrum, and that is, in a broad sense, what are some of the technologies that we can develop, in this case with Siemens working with partners. You'll be hearing from Trent a little bit from KC8, which is in the area of post-combustion capture, taking flue gas off an existing emitter, stripping that, and from there capturing the carbon. And one area of my one slide that I have today will cover the area of oxy-combustion or direct combustion. And this is an area that Siemens is working with 8 Rivers. And we've been in that process now for about 2 years with development. We have a very large team committed from Siemens Energy as a strategic partner. And in developing a direct combustion, which means we're taking artificial air that comes via an air separation unit. We're basically combusting that in a very CO2-rich environment. And you could think of that as ultimately firing combustion within a supercritical CO2, very high pressure environment. We're talking about 350 bar. And if you think of CO2, isn't that an extinguisher used in a lot of industrial applications, buildings? You're correct. So there's a lot of things there that we're really pushing the limits in how both CO2 should be behaving, how we maintain both an intermittent and also a prolonged firing, and yet with the hope of gaining an efficiency similar to an air-breathing F-class gas turbine, for instance. So the size of turbine that we're developing currently is equivalent to an F-class turbine, so about 500 megawatts thermal, and output of roughly 250, 280 megawatts electrical coming out of that. And as you correctly pointed out, in some of the front end for anything involving CCUS, you have a parasitic load, and we carry a parasitic load for this in respect to the air separation. In applications such as with KC8 on the post-combustion capture, you have a parasitic load that's running for compression and taking your heat from which to run the solvent. If you're looking in the case of blue hydrogen and trying to create through an SMR, you're doing much the same. You've got a condition coming in for the stripper agents that takes energy in. And for us, we're very focused on how we can get that process as efficient as possible for getting a levelized cost of electricity out of the back end that can be somewhere in the 2 to 6 point range, comparing that to traditional air-breathing turbines today with natural emission as flue gas. And to do that, and this is the turbine that we're looking at, that we're developing here currently. This will be agnostic to any type of fuel source. So we'll run across the whole APA range. The first applications that the team and I are working on is primarily with syngas. So for that, we don't see coal going away quite yet. And one of the ways that we're justifying this is basically on an entire replacement of an existing asset. So it's not just adding technology onto the back end and then stripping off the CO2 and then sequestering that. What we're essentially doing is also replacing with an entire new value on the power generation island, and we're sequestering the CO2 out the back end. And at least in this business case, I'll leave you with several other thoughts to think about. You know, from what I mentioned earlier, you need to think about everything that you're emitting, as well as we know there'll be higher OPEX and CAPEX going into the front end of this. And so in everything that we're able to separate as part of this CO2 concentrator, which can also take in flue gas, you can put this on the back end of other emitters, take in other CO2 emitters. But as far as the combustion process, we're basically recirculating CO2. We're concentrating that to a supercritical state under pressure while maintaining a sustained fire. And from that, with air, you're separating your oxygen portion, which we're using. As part of the process, there's also a separation of argon and nitrogen. And so I would subscribe, those are two areas coming in a very ultra pure state, which in turn we monetize as part of the business case. In addition, this particular, in a combined cycle type of mode, generates a lot of water. So when you take conventional thinking of what's between air and fuel, what are your two big requirements for an air-breathing gas turbine? Water. So there is no water required in this process. So that's a little bit of just, I want to share with you one example where we have to take a little bigger view from a business case and not just one-dimensional, as I had always been trained with levelized cost of electricity, to pull that together into an entire project. As far as projects right now, we have 14 feasibility studies that we're conducting. All of them are in the CCUS space. To be successful in CCS and CCUS capture, you need to have proximity to a delivery mechanism. So however you're capturing it, you need to be within close proximity to either a Class 6 well, so you can sequester direct into the ground. That limits your market considerably. You need to have a proximity realistically to pipelines for a delivery vehicle. And you would need compression on the back end to get that to pipeline level pressures. So in closing, I want to leave some time with Trent here and the discussion on post-capture. I'd like to close that proximity is key. You need to have proximity to a market for CO2. And if there's some question, well, how about the U.S. energy policy? Does that put any of this in question? Perhaps. But I'll also mention that this is not for every backyard where you have a power plant, where you have an emitter. You have to have proximity to the offtake demand for CO2. And so we're primarily focusing on areas where there are existing pipelines. For instance, I track every well permit, well status that's going in, and those are all ideal candidates for an area. And I think also looking at markets where you have oil-producing states, which is really set right now for a bit of a renaissance again with respect to using CO2, because CO2 has some marvelous capabilities for scrubbing in concert with other ways of extraction of oil. There is a real and growing market that we foresee for CO2 in the EOR space, and that's for production of oil. So what does that mean? I think just talking CO2, for instance, for us, for an F-class gas turbine, which we'll be working with KC8 on retrofit of air-breathing turbines, say an F-class turbine of about same size as this in output, 200 to 300 megawatts, we're looking from roughly about 2.5 million tons per annum. Now, if that same amount of CO2 is being applied for enhanced oil recovery, usually that's about 1 ton of CO2 for every 2 barrels of oil. And so you can look at that in oil-producing states as really a tremendous demand. And we're seeing that right now actively in 8 states where there is a market irrespective of what the capture rate for sequestering CO2. And we see that to continue. So with that, I want to be timely here. I'm working for a German company. I got to be on time. So I'll turn that over, and any questions, happy to entertain later. Thank you.